These slides will talk about formation constants, or K sub F. Our lesson objectives: we'll define coordination complex, coordinate covalent bond, and ligand. We'll apply Lewis acid-base definitions to coordination complexes, including Lewis acid, Lewis base, and Lewis acid-base adduct. We'll review coordination complexes from lab. We'll define a formation constant, K sub F, for coordination compounds. We'll define a dissociation constant, K sub D, for coordination compounds. And we'll perform equilibrium calculations involving formation constants. Ions or molecules located around a metal center are called ligands. Coordination complexes are made when a positive metal center attracts a ligand, which is a chemical species containing lone pair electrons. They form a coordinate covalent bond. So, coordination complex is metal plus ligands. A coordinate covalent bond is one in which one species brings both electrons to the bonds. The metal ligand structure is called a coordination complex. So now let's merge this with our Lewis acid-base vocabulary. So the metal cation is a Lewis acid. The ligand is a Lewis base. And the complex that forms with the two of those together is a Lewis acid-base adduct. Look at that. A little bit of inorganic chemistry. We've been dealing with Lewis acids and bases for 2 terms of lab now. We'll get into more of that in the coming slides. Let's finish out our definitions. A complex ion is a charged coordination complex. So you put a charge on a coordination complex, you can call it a complex ion. So let's talk about an example. Silver plus thiosulfate makes silver thiosulfate complex. The thiosulfate is the Lewis base, the silver is the Lewis acid, and the silver thiosulfate is the Lewis acid-base adduct. You can see that the thiosulfate has many lone pair electrons available. When we put the silver and the thiosulfate together, the sulfur and the silver form a coordinate covalent bond, and we get a silver thiosulfate coordination complex. So what other coordination complexes have we encountered? Let's go back to lab. You have experience with these from lab. Lots of inorganic coordination complexes in lab. The first one you encountered, though, was in the gravimetric analysis lab, where you used alum, which is actually also a double salt that has 2 different cations involved. So here we have my sketch of the structure. It's not great, not by any means, but it's functional. So we have aluminum 3+, that is a Lewis acid. We have sulfate, which is a Lewis base. And in this complex, potassium aluminum sulfate is a Lewis acid-base adduct. You'll note it has a tetrahedral structure, and we have a bidentate ligand, meaning it binds in more than one spot for the single molecule. So we have it aluminum bound to sulfate in 2 different places. In the lab practical, you used iron ferrioxalate, and here again we have a relatively crappy but somewhat functional sketch of the structure. We have an iron 3+ center, that is a Lewis acid. We have oxalate, 3 of them around the outside, that is a Lewis base. And the whole thing together is a Lewis acid-base adduct. And again, we have a bidentate ligand. In this case, we have an octahedral structure. Let's go on to the next one. From this term, you did a cobalt-3 coordination complex where you had ethylene diamine, and it formed a complex with cobalt. So ethylene diamine is the NH2 with that like boxy thing going on. Those are carbons, in case you're wondering. That's a line structure. So it's N, carbon, carbon, N. Again, bidentate ligand. The ligand is the Lewis base, the cobalt is Lewis acid, and the cobalt-3 ethylene diamine complex is a Lewis acid-base adduct. Are you starting to see a pattern forming here? Hopefully. you've picked out that the metal is always a Lewis acid, the ligand is always a Lewis base, and the complex is always a Lewis acid-base adduct. Now that we know how to form a complex, let's talk about the formation constants, or K sub F. They give the equilibrium constant for coordination complex formation. So if we go back to our example from the previous slide with our silver and thiosulfate, our K sub F is products of reactants. The coefficients become the exponents. So for silver and silver thiosulfate, they're both to the first power, and we don't bother putting that. But for thiosulfate, we put it squared because we have 2 thiosulfate for every one everything else. So make sure that you remember to make the coefficient the exponent when you put it into K sub F. Now, it turns out you can also flip this equation. The opposite of formation is dissociation, or K sub D. So if you flip the formation equation, you get a dissociation equation. The dissociation constant, K sub D, is the equilibrium constant describing how the coordination complex dissociates. So if we have silver thiosulfate becoming ions of silver and thiosulfate, then K sub D is the thiosulfate squared times the silver over the silver thiosulfate. Now, hopefully, we remember from before that K sub F is the opposite equation, and it actually is the inverse by observation of K sub D. So if you take the inverse of K sub F, you will get K sub D. Anytime you flip reactants and products, this relationship will hold true, and we'll talk more about that in the coupled equilibria slides.
All right, so this is a reminder of simple calculations you can do with equilibria constants. So we're going to calculate Kf from a bunch of molarities. What is the Kf of copper to cyanide if concentrations at equilibrium are as follows? Copper 2 plus is 8 times 10 to the negative 7th molar. Cyanide is 6.4 times 10 to the negative 6th molar. And copper cyanide is 1.3 times 10 to the negative 2nd molar. So we're going to take the Kf equation, products over reactants, right? So we have the Lewis acid-base adduct, the complex, over the Lewis acid and Lewis base. And we take the fact that we have a subscript of 4, and we use it as a superscript when we put it into the Kf equation. All right. When you put that into your calculator, make sure you use the correct parentheses to get the right answer. In this case, it's 1 times 10 to the 25th.